Mr. Doolin, I thank you for tuning in. Today what we're going to do is we're going to take a look at calorimetry. Calorimetry is the process of measuring heat energy based on observing changes, all right, that occur when one body absorbs or discharges heat to another, all right? We understand and we learn from Gibbs Energy that we get this energy transfer, and generally we go from areas of high energy to areas of low energy. And so what we're going to do is we're going to manipulate this and be able to do some calculations to be able to quantify this amount of heat. Now, heat is generally referred to or abbreviated as the variable Q. All right? So a positive Q means I have absorbed heat. A negative Q, so positive Q is absorbed heat. A negative Q means that I have lost heat. All right? So again, we're relating these back to endothermic and exothermic. All right, the equations that we're going to use for this, because the amount of heat that can be exchanged is dependent on the amount of mass that's there, and not to mention the amount of inherent energy, the heat energy that's in any particular system because of the type of molecules that are there. All right, so we've got a couple of different variables that we're going to use here. Now, the equation that I refer to always is MCAT, right? MC, this delta looks like an A, and then T, so Q equals MCAT. All right. And in this particular case, M is the mass of my substance. The units of this are going to be grams. The specific heat capacity, you do want to understand what specific heat capacity tells me. The specific heat capacity is defined as the amount of heat energy it takes to raise the temperature of 1 gram of substance 1 degree Celsius. So again, it's the amount of heat energy that's needed to raise the temperature of a substance, 1 gram of substance, 1 degree Celsius. And so it really gets into the fact of what is this particular substance, what are the intermolecular forces that are holding it together, how easy or how difficult it is, how much energy it requires to actually speed up and get those molecules moving. All right? So that's what specific heat capacity is. It can also be referred to as molar heat capacity. And so if your specific heat capacity, I guess let's look at this. Let's see, our C value is grams per, actually no, it'll be joules, right? Because the amount of energy it takes to raise 1 gram of substance 1 degree Celsius. And so that's going to be my normal specific heat capacity units, is joules per grams degrees Celsius. Now, I also have a molar heat capacity. And in this particular case, it's still the amount of energy, but instead of grams, now I've got moles, and it's still to raise 1 mole of substance 1 degree Celsius. And so the difference between specific heat capacity and molar heat capacity is really just a units kind of problem. All right? Okay. Now, states of matter also do come into play when I'm looking at specific heat capacities. Now, the C values, they are going to be table values. They'll be given to you. The only one that's not really given to you is the specific heat capacity of water. And that is actually 4.18 joules per grams degrees Celsius. And that's a number that you will actually have to know. In calories, that is actually 1.00 calories per grams degrees Celsius. And so these are actually two values that you will need to know. Not to mention it gives us the conversion between joules and calories. You can see that 1 calorie is actually 4.18 joules if you knew both of those. All right. So, a couple of assumptions that we're going to be making in calorimetry is that heat lost is equal to heat gained. We are not really going to pay attention to the amount of heat that's lost to the environment. We're not going to account for it. We know it exists. We know as we move on and get more advanced with our chemical skills and chemistry skills, we can come in and actually calculate those values, but we're not going to worry about here. We're going to assume conservation of energy, so the amount of energy lost is the amount of energy that's gained. So again, if I go back and I put a hot piece of metal in water, the metal's going to lose energy. The water's going to gain the same amount of energy that's lost. They'll just be opposite signs. Okay. So, what is a calorimeter? A calorimeter is essentially just an insulating device. So, with what we're going to do is, don't get too complicated here, is that we are going to have a couple of coffee cups, a couple of styrofoam coffee cups, that we actually just put one inside the other, and that's going to be our coffee cup calorimeter is the way that we're going to refer to it at. Now, a couple of things. The pressure is constant for a coffee cup calorimeter, because the reaction that we're going to be looking at is going to take place under atmospheric conditions, right? Our little bitty reaction inside of a coffee cup is not going to change the atmospheric pressure in a room. So we assume for our coffee cup calorimetry that we are working under a constant pressure. Now, why does that become important? It becomes important because Q is actually equal to delta H as long as we are at atmospheric pressure. If we're at constant pressure, we know that that is actually a true statement. All right? And so again, this gets us back to the question that some people have asked, well, Mr. Doolan, where do we get all these enthalpy values? Well, a lot of them is we get them from the calorimetry. We apply this constant pressure calorimetry, and we can actually figure out these enthalpy values for our reactions based on the heat exchange of a reaction with water inside of the coffee cup. All right? And that's normally what we're doing, because we'll stick a thermometer inside of this coffee cup, and we'll have water inside of here, and we'll perform our reaction in that aqueous environment, and we'll measure the temperature change of the water. And so then we can actually calculate Q equals MCAT of the water, right? And so that would be, most of the time, this is heat gained by the water. And so we've got Q of H2O, and then that's going to equal the negative Q of my reaction, assuming my reaction is an exothermic reaction. All right? And so again, it's just, if my water is going to raise in temperature, it means my reaction is losing heat, my water is gaining heat. If my water temperature, it is possible for the water temperature to actually go down, right? And so if I see a decrease in temperature, that means my water's losing heat energy, and my reaction is gaining that heat energy, and that would be an endothermic reaction. Okay? All right, so hopefully not anything too crazy for you, ladies and gentlemen. Big thing to understand is that Q is equal to my delta H, that enthalpy value. We are going to be working under constant pressure. Heat lost is equal to heat gain. And if you have any questions other than that, please get them down. I'll see you in tutorials. Other than that, I'll see you in class.